This is an actual exam I gave in my statistics course. This exam 3 is about regression analysis and multiple regression. A biologist captured 9 sand female sand fleas that had eggs. After counting the eggs, the biologist froze the sand fleas to get their accurate weights, and what he wants to know is to figure out if there's a linear relationship between the weight of the sand fleas and the number of eggs it holds. Sounds reasonable, right? Okay, so first find the correlation coefficient using your calculator. And what you need to do is to put all these numbers into the calculator by first turn it on, and then let me just clear this. Quit. Oop. All right. First, stat, and if you edit, it allows you to edit the lists. And I here put all the numbers in to save time. So once you put all these numbers in, by the way, if you go way up to the list and then hit clear and then enter, then the entire list can go away. That's another thing that could help you if you have many other lists before you put in this. Okay, well, anyways, we quit, and then now that you have the list of the weight and the eggs, and you're trying to make the second list 2 should be the y, and list 1 should be your x. And once you have that done, then you can go to stat, and you have to do the regression test. If you go way down, there's the linear regression test, and there are 2 tests, and the one that you want to use is the first one, the t-test. So if you apply the regression t-test, just don't touch anything. It's just default is L1 and L2, which is what you used, and then just calculate, enter, and then it gives you all the values. And if you scroll down, you'll see that you get the correlation coefficient R, and also the regression equation is y equals to a plus bx, with a being this number and b being this number. And it even gives you the degrees of freedom, which is 7. So it gives you all the answers. So I can populate the answers now. R is 0.8739. That's the correlation coefficient, either capital R or lowercase r. And then regression equation, I just simply wrote a plus bx with the value of a and then value of b. That's all I have. And the degrees of freedom is 7. Now the formula for the degrees of freedom is really the n-2 for regression. So this is n-2. Okay. Degrees of freedom is n-2 when it comes to simple regression. Now in multiple regression, when you have a lot more predictor variables than just one, then you keep subtracting more numbers as you increase your predictor numbers. That's going to come up in another question, so I'll talk about it later. All right. Now, part D, it says, determine by the row test if there is a significant linear relationship between whether there is a correlate. Oh, sorry, determined by the row test if there is a significant linear relationship between the weight and number of eggs at 0.05 significance level, and the question is, you must justify your conclusion using the row test. Okay, so how do you do that? Well, I do see that 0.8739 is quite close to 1, and you would expect that this is indeed a high value, so you can say it's correlated, but what is the significance? So you actually have to do a statistics test where the null hypothesis says there is no linear relationship between the two variables, And this is really saying that the regression that you're seeing here is just by chance. And the actual correlation is 0, but somehow these values appeared by chance. That's your null hypothesis. But if it's determined that this value is too high to be thought to be made by chance at 0.05 significance level, then you have to choose the alternative hypothesis, which says that there is a linear relationship between the variables. Okay. In other words, rho should not be 0. All right, so let's see who is right. To know that, you have to figure out the 0.05 significance level at degrees of freedom 7. So let's look at the Pearson R. So this is called the Pearson correlation coefficient. So Google Pearson correlation coefficient R table, or Pearson R table, then you'll see this. And as you can see here, you have alpha equal to 0.05, and degrees of freedom 7 is 0.6664. Okay, and because since R equals to 0.8739 is above 0.6664, it means that it has higher correlation coefficient than the threshold, so we do see a correlation. So we can say that since R equal to 0.8739 is above 0.6664, we reject the null hypothesis and determine that we have sufficient evidence to accept that there is a linear relationship between the weight and number of eggs. So that's how you say it. Okay. All right. So that's I put another row test a little later, so I'll do that again. See if you can do the next one and see if it's easier there. All right. Second question. I have a bunch of questions independent of others. There's some small items. Each were given 5 points each. What range of values can coefficient of determination be? Now, you have to know what this word coefficient of determination is. This is really not R. R is correlation coefficient, okay? It's R squared, okay? So coefficient of determination is R squared. And because R, since R is between -1 to 1, we know that R squared must be between what? Is between 0 and 1, right? Because if you square a -1, it becomes +1, so it's this one, okay? So you have to watch out. Sometimes I'll be asking coefficient of correlation. In that case, the answer is the -1 to 1. Sometimes I might ask coefficient of determination. That's R squared, so it's between 0 to 1. All right. Now, if 53.2% of variation can be explained by the regression equation, what is the correlation coefficient? Okay. So to add to this first question, the meaning of R squared is really the proportion of variation of y due to the regression equation. Okay. So this sentence right here, since it's saying that the 53.2% of the variation, it didn't say why, but it really, what else can it be, right? So since 53.2% of the variation of the quantity can be explained by the regression equation, that means r squared is 0.532. Okay, so we see that r squared is equal to 0.532, and that means that r would be the square root of 0.532. So let's try that. Square root of 0.532, and I get 0.7293 or 0.7294. But one thing that you have to be careful is that correlation coefficient, since r could be between -1 to 1, it could also be negative. So the answer should come out as plus or minus 0.729. Okay? Yeah, so here. So r should be plus or minus 0.7294. Okay. Part C, 1999 data of 8th grade pupils in Netherlands has the following data: language test score, verbal IQ, number of books read per month, ID number, and economic status. If multiple regression is to be performed to predict the language test score from other data available, which variables can be used as the independent variable, or which cannot be used as an independent variable, which can be used as a dummy variable. Now, see, we're trying to predict the language test score, so that's the value of y, and therefore it cannot be the predictor. Okay, you can't use language test score as one of the predictors. That's out of the question. So what's left? There's the verbal IQ. Can verbal IQ become a predictor for language test score? I guess it would have some influence, right? So I would give it a go. Okay, so I'm going to put verbal IQ here. Right. And then how about number of books read per month? You would expect that the more books that a person reads, it will do better on the language score, right? Language test. So I would accept this one. How about ID number? Well, ID number is just assigned randomly, so it has no bearing or no meaning to the person. So in this case, this is the data that you should never include in your linear regression, because this has nothing to do with your language test score. If this does come up significant somehow, then either there's some kind of a method used in assigning an ID number that made that happen, which doesn't seem, usually that's not the case, or it could just be some correlation that just happened just by chance. So unless you have a good reason to believe that there could be some kind of a logical thing that correlates the two, especially for random numbers like this, you should never include it. Okay, so that should be something that cannot be used as an independent variable. And for this economic status, well, it's either above or below the poverty line, so it's not a numerical value. But however, you can use something called the dummy variable or indicator variable to put that as one of the inputs, because you would think that, oh, maybe people with higher economic status have more access to the library and other things that they might have better chance of achieving higher language test score, right? So you do want to include this, and therefore when you actually run this multiple regression analysis, what you're going to do is you would put 1 for above poverty and 0 for poverty. Okay, so if it's above the 180% of the poverty line, you would put 1, otherwise you would put 0. And if you do that, you would see some kind of correlation between this economic status and the outcome. So that's something to be used. And such a variable is called a dummy variable. Okay, now determine which correlation coefficient shows the strongest linear correlation and justify your choice. And the highest number here is 0.729, but the negative 0.851 is even closer to -1. So I would go with D, and the reason is the stronger the correlation is, the absolute value of the correlation is close to 1. So the absolute value of negative 0.851 is 0.851. That's bigger than 0.729. So this one has stronger correlation. Okay, and then from a wage data of 758 individuals, this is the multiple regression, and it's asking us to predict the monthly income of a year 1980 of a person with 14 years of education that earned associate degree and has 5 years of experience. So this is what you have. Okay. Now there was something that I forgot to put in this question. I should have said that the multiple regression F test came out to be significant, so that it justifies our use of this. If the F test for multiple regression came out as not significant, then we cannot use the multiple regression equation, but rather we will have to just use the average of the wage data to be our best guess. Okay, so this is very important. Okay, so only when your multiple regression or simple regression comes out as significant. Multiple regression you use F-test, and simple regression you use road-test. In those cases, you have to you may use the regression equation to predict it. So so assuming that, we can just plug in the 14 years here and then 5 years there, and you compute this, and that's the answer. Okay, so 893 was the answer. Question 3, from the historic data of the average annual temperature of the Central Park, and I guess it's really asking whether there is global warming or not, right? And there seems to be some correlation between the years and the temperature, so there's a linear relationship, which means that as the years go by, the temperature change is gradual according to the years. And actually, if you look at the coefficient of x1, this is positive, so and also this is positive, so it's positively correlated, which means that as years go by, the temperature goes up. So this is a pretty important or very compelling evidence that there is global warming. Okay. All right. So determine if there is a significant linear relationship between the variables by the road test at 0.05 significance level, and as we already have done one road test before. The road test requires the null hypothesis as having no correlation, rho equal to 0, and H1 as rho not equal to 0. And then degrees of freedom is n minus 2. And actually that's really, if n is not given, it's the residual degrees of freedom. Okay, so residual degrees of freedom is the degrees of freedom for simple linear regression. Okay, there's also the degrees of freedom for the regression, and that is actually same as just the number of variables. So in simple regression, you just have one predictor, the years, so that's why it's 1. Okay, so because residual here is 4 and that's n minus 2, it looks like we have 6 entries of data. Yeah, and seems right because it's 60, 70, 80, 90, 2000, 2010. So that's 6. Okay, so you can also have it that way. So anyways, we have the degrees of freedom equal to 4. And we can also see that the row critical is 0.8114. Let's look at the from the row table. So here's significance level 0.05, and at 4 degrees of freedom you have 0.8114. Okay, so at 0.05 significance level, row critical is 0.8114, and therefore since our R value, this is greater than the critical value, we conclude that there is a significant linear relationship between the variables. Okay. Part B, what percent of variation in time is explained by the regression equation? Well, that's coefficient of determination, right? Coefficient of determination determines how much of the variation is due to the regression equation. And since it's r squared, you can just take this r value and you can square it. So all we need to do is just take this value and square it. Let me show you 0.91356 squared, and you get 0.83459. So that's the value. Now, alternatively, you can also do sum of squares of residual, sum of squares of actually not residual, regression, sum of squares of regression out of the sum of squares of the total, because these are both some quantities before divided by n equals to 6. So if you divide both by 6, the ratio is still the same. The ratio is still this. So what it shows you is that this is proportional to the variance due to the regression, and this is proportional to the variance due to variance of the actual data. And this ratio will tell you how much of the variance of the entire thing is due to the regression. Okay, so if you take this value and you divide, you will get the same answer. So let me show you. If you do 2.12280 divided by 2.54348, then you get almost the same answer. I didn't put enough digits, but if you put more digits, it will be the same. Okay, so I would say 0.8346 is the answer. Okay, so that's the answer. C, find the regression equation and predict the average temperature of the Central Park in years 2020 through 2029. And see, this is a simple regression because there's only one predictive variable. If this is 1, that's a simple regression, and you can also see that there's only one variable for predictor. And these two values are b0 and b1, where the equation is b0 plus b1x. And so if you use this y hat equal to b0 plus b1 times x1, this is the linear regression equation that you get. Okay. Uh, Now, since the road test we had in part A was significant, we may use this to predict the temperature in 2020. So, uh, according to this data, the average temperature of uh, the Central Park uh, would be in in the 2020 through 2029, it would be about 56.35. Okay. All right. So this value actually tells you how much temperature would change every year. So every 10 years, it will be like zero point 0.3 Fahrenheit that's increasing. Uh, yeah. It still sounds smaller than what global warming scientists are saying. But I guess in other places it's bigger. Okay. All right. So that's the answer to part C. Oh, this is unintended. All right. Next question. Actually, the last one. For students in a statistics class recorded resting pulse rates in class. They provided additional information about height, weight, and hours of exercise per week via a survey. So this is a multiple regression with three predictors: exercise, height, and weight. You might have heard that people who exercise a lot have slower resting pulse rate. So you kind of expect that this would do something, but overweight could be a factor as well. So you put these two things as another factor, and we ran the multiple regression, and if you do that in Excel, you get a bunch of numbers, and this table was obtained from Excel, but I erased some of these values so that you can figure them out. Okay, so it says fill in the MS for regression and residual. Use it to find F statistics and the overall significance of predictor variables. Now, SS means sum of squares, where you take the difference between the data value and the average value, you square them, just like how you do variance. The only difference between variance and sum of squares is that for sum of squares, you don't divide by n. Okay? And MS is the mean sum of squares, or mean squares. And the formula for MS is simply you divide the sum of squares by its degrees of freedom. So this divided by 3 will give you the MS for regression. This divided by 24 will give you the MS for the residual. Okay. So what I did was I plugged these into the calculator and I got these values. I can now use these to populate these two places. Yeah, and you don't need the MS for the total, okay? Although you could, yeah. You just need these two. And then I need to find the F distribution. F statistics. So I have to do an F test, and the test statistic for the F test is called the F value, and it's defined as the ratio between these two mean squares. Okay, so this one over this one fills in this blank spot. Okay, so here are 3 values, and then now you only have 2 values, and this last one you only have 1 value right here. Okay, so if you actually ran the Excel linear regression sheet, you'll see that it only has one number here, and that number is simply you divide these two, 4.744, you put that in there. And now let's think about what this means. Well, there are 2 ways to go about this. One is to look at the F distribution table and find out the critical value at 0.05 significance level, and then try to find what the critical value is. But here, it's asking for overall significance. So it's really asking for the p-value. If you ran the Excel, the p-value falls in right here. But how do you get it without the Excel? Well, here's how one gets it. The p-value is the right tail, and the right tail, to get the right tail, you have to do 1 minus the FCDF, the CDF cumulative distribution function for the F distribution. And you put this number in, but F distribution requires 2 degrees of freedom, the degrees of freedom of the numerator and the degrees of freedom of the denominator. So you have to put those 2 numbers in, and those 2 numbers are just given here, 3 and 24. So what you can do is you can just execute this on your calculator. So let's try this. So you want to do 1 minus, and I need the FCDF, so second distribution, and you go to FCDF right there, and don't touch the lower, just punch in the upper as 4.744, and the degrees of freedom of the numerator is 3, degrees of freedom of the denominator is 24, and you paste this, and the value is 0.00977. Okay, so that's the p-value. So even at 1% significance value, it's still significant. Okay, so it has a very small number. Okay, so that means that the linear regression equation we got is useful, right? Okay, so that's the value that we have. Now let's move on to B. Find the influential predictor variables at the 0.05 significance level. Well, even though the overall linear regression came out as significant, some of the variables might not be that useful. So you can see that from the p-value for each individual values, and here it says 0.002255, so this is extremely significant, but these values are quite high, so these are not significant. So the only value, only p-value that's less than our 0.05 significance level is this exercise, so the answer for this will be just exercise. Okay, what percent of variation of pulse rate is not explained by the regression? Well, so this is really asking about something like the coefficient of determination, except that coefficient of determination, the R squared, gives you the regression sum of squares divided by the total number. However, it's not, so it's the opposite. So the residual is the random component you get after subtracting the regression equation, the ones that cannot be explained by the regression equation. So you take this and divide by the total, that gives you the R squared. So even 1 minus R squared. So even if R squared is not given, if R squared is given, you would do 1 minus R squared. But in our case, it's simply the sum of squares of the residual divided by sum of squares of total. Note that R squared itself is sum of squares of regression divided by sum of squares of total. Okay, so this is what we have to compute, which means you have to do 1684.901 divided by 2684.107. So let's try that. 1684.901 divided by 2684.107, and the value is 0.6277. Okay, so the answer is 0.6277. Part D, construct a 95% confidence interval for the true coefficient of exercise. This coefficient right here, these are all estimates because we don't have the data for everybody. It's just students in one class. So if you're interested in all the people in the college or all young men in the state or something like that, if there's a bigger population, these numbers, these coefficient will be still some kind of an approximation, right? It will come with some error, and our interest is how much can this vary, right? And to do that, you first have to understand that this is the value, the point estimate of the coefficient, and this 2.21 is the standard deviation or standard error for this one. So that's SB1 2.212279. Okay, and what you do is the margin of error depends on the confidence level or significance level you choose, right? And because our residual is 24, and this is not bigger than 30, we have to use the t distribution. If this is really big, then you can just use z distribution. Let's say if you have like 40 or 50 residual degrees of freedom, then you can use just the z, but here it's less than 30, so we have to use a t distribution. And the way you get the t critical value is same as before, except that instead of using n minus 1, you actually have to use n minus 1 minus k, which in this table is just 24. Okay, so maybe I should make a note here. Note degrees of freedom for the for t distribution is degrees of freedom of the residual, which is equal to n minus 1 minus k, and because k is 3 in our case, right? And it didn't say how many, but the total is n minus 1, so we know from here, we know that the entries in the data is 28, so if you do 28 minus 1 minus 3, you get 24. So that's how you got 24. If you're curious to know how Excel gets the 24. Okay, so we have that, and now you have to go to the t distribution and find out the critical value for you can go to the t distribution table with 24 degrees of freedom and then find the critical value for the t distribution, or you can also use the calculator. So I like to use the calculator. So t alpha over 2 is inverse t. So you go to second distribution, go to inverse t, and you do 1 minus. Since confidence level is 95%, the significance level is 0.05. So you do this and divide by 2. Degrees of freedom is 24, and if you paste this, you get the value of 2.063. Okay, so that's the critical value, and since we have all the values, we can now calculate. Okay, so 2.063, you multiply that with the SB1 using this right side formula, and now you get the margin of error, which is this one, and negative 7.5617 plus or minus this value will give you the confidence interval for this coefficient of exercise. Okay, so that's the answer.